NVIDIA finally enabled the pre-order of the new NVIDIA DGX Spark, formerly known as Project Digits, and unveiled more of the specs. I made an entire video about the Project Digits and expressed my excitement for having a tiny machine being capable of running large language models with great performance without having to rely on the cloud. However, time passed and things happened to make the Spark not as stand out as much as it did before, and we should reevaluate the value proposition. I mean, we not only get a new Mac Studio M4 Max and an M3 Ultra with 128 and up to 512 GB of RAM. We also saw the framework desktop being revealed with the new AMD Ryzen AI MAX Plus 395 and 128 GB of soldered RAM for slightly above $2,000. And finally, Serve the Home tested a new budget option from Acemagic with an AMD Ryzen AI 9HX 370 processor that could be populated with up to two 64GB modules for a total of 128GB available RAM. You could get that system for just about $1,200. There are even more contenders out there right now, and I'm not going to go into that. This is just a sample representation of what I see out there in general. It's a very interesting time, but with so many options, the question is, how do these machines compare, and is one of them maybe an option for you? As you will see, this is not black and white. Vendors trying to sell their products by, let's say, highly optimized benchmarks, it's not helpful either. So this is going to be a fun video. Before we get into it, however, I want to thank all of you who watched my previous videos and engaged with me in the comments. Thanks for your feedback, it's greatly appreciated. Also, I like to share some thoughts on the end of each video, so be sure to check it out if you're interested in my take of things. Okay, back to the topic. Let's start with looking at the core specs of the systems to get an idea what we're dealing with and then compare some of the aspects in more detail. As always, all links and sources are in the description along with chapter markers to jump around in the video. I don't want to take you hostage and waste your time. First up, we start with a new NVIDIA DGX Spark. Here we get the new Grace Blackwell GPU with 128GB of low-power DDR5X system memory and a 20-core ARM CPU with 10 performance and 10 efficiency cores. We also get 4 USB ports, no Thunderbolt unfortunately, but 10GB Ethernet, Wi-Fi 7 and Bluetooth 5.3. On top we have the ConnectX-7 Smartnic for high-speed connections to directly connect another Spark. Not sure if this is the 400GB connection or a stripped down version though. Storage could be either 1 or 4TB. That's all the customization you get, which is unfortunate, but I'll get to that one later. All of this comes at a max power draw of 170 watt. The system is not out yet, but it'll cost you between 3 and 4K, depending on the SSD size only. For the Mac, we basically have two systems, the M4 Max and the M3 Ultra. Configurations range from 14 to 32 core CPUs, 1/4 being performance cores, 32 to 80 core GPUs, 36 to 512GB of unified memory, and 512GB to 16TB of SSD storage. We also have 6 USB ports, only 4 of them being USB 5 on the M4 Max compared to all 6 of them being USB 5 on the M3 Ultra. All Mac Studios feature 10GB Ethernet and Wi-Fi 6E, as well as in Bluetooth 5.3. The wattage is not as low as the Spark, but averages around 60 watts in many cases, although the PSU supports up to 480 watts for the M3 Ultra and 370 watts for the M4 Max version. The price of the system ranges between 2K up to over 14K. A more fairly comparable system, however, will range between 4 and 6K. Man, those SSDs are pricey. The framework desktop and the Acemagic F3A represents AMD's new Ryzen AI series chips. The Ryzen AI MAX Plus 395 is a 16-core Zen 5 CPU combined with 14 compute unit RDNA 3.5 GPU and an integrated XDNA 2 AI engine NPU, delivering 50 plus TOPS. It's essentially a laptop chip tuned up to 120 watt CTDP in a desktop. Notably, it supports up to 128GB of unified LPDDR5X memory. For the framework, the unified memory is soldered on and not upgradable, but the integrated GPU can dynamically use up to 96GB of VRAM of it. similar to other contestants. The Ryzen AI 9 370X, however, is a cut-down variant, a 12-core CPU for high performance and 8 efficiency cores, and a smaller RDNA 3.5 iGPU with only 16 CUs, branded Radeon 890M. The odd difference is that the Acemagic F3A features a maximum of 96 GB of VRAM, but the actual chip could support up to 256 GB with its 2 memory channels. An interesting tidbit for an inferior model. The framework is a mini ITX form factor PC and even includes a PCIe 4.0 X4 slot, whereas the Acemagic is a palm-sized box, NUC style if you will, with no internal slots. Both have ample connectivity. For example, the Acemagic F3A offers dual 2.5 gigabit Ethernet NICs, 2 M2 VME slots for USB 3.2 Gen 1, and 2 USB 4 ports, Wi-Fi 6, Bluetooth 5.2, bundled in a TDP of 54 watt. The framework also offers 2 M.2 VME slots, 2 USB 3.2 Gen 1 and 2 USB-C ports, Wi-Fi 7, 5 gigabit Ethernet and various expansion cards with a TDP of 400 watt. At least that's what the power supply supports. The bare bones Acemagic comes in at $679 on sale or $959 regular. With a 1 or 2 terabyte SSD and 96 GB of RAM, we are still below 1K on the sale. The framework could be configured in multiple options, but one with the best CPU and 128 GB of RAM and a decent SSD ends up at around $2,300. Great. Now you have all the facts and you know exactly what model is perfect for you, right? Right? Well, as it turns out, it's really difficult to objectively compare these systems based on a spec sheet, and that's what we're gonna look at. So let's not beat around the bushes and dive right into it. One, if not the most important metric currently for inference of large language models is memory bandwidth. So how does these machines compare? First place goes to the M3 Ultra Max Studio with 819 GB per second, followed by the M4 Max with 546 GB per second. The Spark and the Ryzen AI 395 Plus are having a tight race with 279 GB per second versus 256 GB per second. And the Ryzen AI 9 370HX is trailing with lower than, I think, 175 GB per second, depending on the RAM used. Given these numbers, could we simply derive a scaling factor just from these? Is it that simple? Well, glad you asked. So, no, but kinda yes too. It's complicated. As a rule of thumb, you could take the memory bandwidth and divide it by the model size in gigabytes, if it's in FP8 or INT8, to get an upper limit. If the model has half the precision, same size, double that number. So a 70B model in INT4 with 35 GB on disk would theoretically produce with an M3 Ultra 23.4 tokens per second. With the M4 Ultra, 15.6 tokens per second. For the Spark, would be 7.8 tokens per second. The Ryzen AI 395 Plus would be 7.3 tokens per second. The Ryzen AI 9 370HX would be 4.9 tokens per second. Though this one heavily depends on the memory modules and is likely to be closer to half of what the 395 Plus has. Well, these numbers don't look really impressive, but not bad either, at least for the Mac versions. Now, my first question is this generalization actually true? And what does upper limit mean? Fortunately, in the last video, I thoroughly tested my machine and a bunch of cloud version as well. So I have a solid set of reference numbers to compare to. I used the Llama 3.18b Instruct model with 9 GB on disk. Let's start with the A6000 to look at. We have a memory bandwidth of 768 GB per second and 9 GB model. That's around 85.3 tokens per second max according to our formula from before. In real life, however, I was able to get only 43 tokens per second. The A5000, my personal favorite card, has the same memory bandwidth and thus should get the same 85.3 tokens max. In real life, however, I got about 40 tokens per second. So we see the real performance is about half. But where does the difference come from, if not from the memory bandwidth? Well, it's not all about memory, of course. There are calculations to be made, and this is where CUDA comes in. The A6000 has 336 tensor cores, where the A5000 only has 256 cores, more than 30% less cores. What is interesting here is that you do see that cores matter, but not as dramatic as the memory bandwidth. Now, what if we increase the memory bandwidth, further improve the tensor core generation, and also increase the core count? We should surely be better equipped to reach max limit calculations of our system, right? Let's have a look at the A6000 ADA version then. We now have 960 GB per second memory bandwidth that ends up at 106.7 tokens per second max. In real-world tests, I got around 51 tokens per second, less than half the max speed. Our statistics got worse, so it's not as straightforward. We can't just increase the memory bandwidth and scale linear with that, as it seems. Talking about performance increase, going from 43 to 51 tokens per second is a nice increase of around 15% or so, which is great, but not a 2.1 times performance increase reported by the marketing materials found on the NVIDIA website via the chip generation bump. I am sure they managed to get that somehow in some test setup, but for what I care, it's not realistic to achieve these numbers in real-world setups. With all the NVIDIA stuff, I was wondering how this translates to other platforms. Unfortunately, I don't have a massive stack of hardware laying around and waiting for me to test, but I do have an M1 Max MacBook Pro, so I did the same test here. The M1 Max has a memory bandwidth of 410 GB per second, which ends up being 45.6 tokens max. When testing, this ended up being 34 tokens per second on average, which is a way better percentage than the NVIDIA version. It's almost 75% instead of the only 50%-ish of the NVIDIA cards. And knowing that the M3 and M4 generation of chips is even better, this is very promising when talking about expected performance. To be fair, Apple also does some marketing stunts when it comes to LLM performance. The latest claims is this chart. A Mac Studio with an M3 Ultra is 16.9 times faster than the Mac Studio with an M1 Ultra, and still 8 times faster than the M2 Ultra. Wow, these are great numbers. My M1 Max is pretty good, but that would be wow. Well, there's a little reference to the details on the test. As it turns out, it was tested by measuring the token rate using a 174.63 GB model. The M2 Ultra had 192 GB, not enough to fit the model entirely into VRAM of the GPU. So slow CPU offloading had to have happened, and the M1 Ultra even kept out at 128 GB of RAM. How is that a fair comparison? The two other systems had to do inference, at least for some of the layers in the CPU, which is way slower. So not really fair. And with what we've seen from NVIDIA, the bandwidth didn't actually increase, and the GPU impact on inference is not as dramatic. We wouldn't have seen a lot of change between the generations, most likely. Certainly, nothing worth of flashy graphics for marketing sites. To be fair, being even able to run such a big model is in itself a great feat, but I guess not good enough to boost sales in Apple's opinion. So, just to satisfy my curiosity, if you have an M2 Mac Studio and above machine, comment below what the performance numbers you get by running this command here. I'm really curious if I'm right about the performance. Coming back to AMD and their GPUs, although being integrated in the CPU, I don't have an AMD CPU-GPU combo, so this is more of a hearsay than proof. But ROCm support is not widespread compared to CUDA, and NPU support for the AI chip is pretty much non-existent for the masses. And when it is, it's not really faster, but more energy efficient, which within itself is great. But we are not looking for the best efficient, but most capable option. Now we have the AI moniker for two trends, efficiency and performance. As if it wasn't already complicated enough, right? Anyway, on AMD right now, when running LLMs, you basically end up using the mere brute force of the GPU without actually fine-tuning and purpose-built chip optimization usage for LLM inference. So I expect performance to be worse compared to NVIDIA for a comparable memory bandwidth, at least in the beginning. Over time, this will certainly change. But that's what it is, and from what I was able to find out. By the time you're watching this, things might have changed. So please check out the comments to make sure this is still valid. I will try to update the video with information and encourage anyone who knows more than me, please do the same. This brings up the next thing to compare our systems with. TOPS. TOPS are the latest marketing stunt, in my opinion. In short, you should just forget about it. Most of the time, look at this chart. As you can see, the Mac is the worst of the bunch. However, when you look at the performance numbers of the Inference, they do not reflect the reality. This has many different reasons, and I won't be able to show you all, but just give you an idea why this number is basically impossible to compare anything against. Here are some I found. First, what is used to calculate TOPS? AMD offers you two numbers. One for the overall performance and one for the NPU, the neural processing unit. Now, what is actually used when doing LLM inference? Mostly not the NPU, due to the lack of driver support, as noted before. However, when it is used, it is not faster than the GPU, but significantly more efficient, which is great, but not helpful for understanding and comparing system performance. Of the 126 overall TOPS, are these 76 GPU and CPU TOPS, or is this just GPU, or is this calculation even more complex? Because if the CPU is included in the TOPS calculation, I might not want the CPU involved because of communication overhead of my workloads. I just want GPU performance because that's the most optimized usage scenario for me. But what is it? I don't know. When I do want to compare systems, I want to compare them based on the same usage scenarios and not some artificially calculated performance indicators, which brings me to the next one, quantization, and other types of, let's call it, optimizations regarding TOPS. NVIDIA is a great example for that. The Spark is advertised with up to 1000 TOPS, and when you look closer, the footnote states theoretical FP4 TOPS using the sparsity feature. In just a simple statement, 3 different facts are hidden in there. First of all, this is theoretically, so there's no way of telling what real-world performance will look like. I kind of accept that because most of these numbers are theoretical in nature, but you need to remember, this is not measured in a lab. The second one is the, let's call it FP4 feature. In essence, this means the chip could use LLMs with quants of FP4 natively and doesn't have to perform any conversation operations. This is great and all, but this is achieved in a way that when you compare this to FP8 performance, it is half of the performance of that, and BF16 half of that again. So half of 1000 is 500 and half of that is 250 TOPS. But we're not done yet. There's one last thing. The sparsity feature. I'm not going into the weeds of this and even pretend I know enough about it to lecture anyone, but for all intents and purposes, it is sufficient to understand that in an LLM, not all weights are evenly distributed. Many deep learning models can be pruned so that a significant portion of their weights become zero, and zeros could be used to optimize the computation aspect with hardware accelerators. You kind of skip calculating the zeros. This removal of zero values could typically save up to 50% of performance. Great. So with the knowledge that the TOPS are just theoretical and the optimizations gained via the sparsity feature is typically 50%, our remaining 250 TOPS get slashed in half. Our remaining 125 TOPS are still pretty good, I'm not gonna lie. but compared to the other contenders, not even nearly as impressive as before. Now, compare this to the minuscule impact of the GPU performance compared to the bandwidth. TOPS are not really helpful at all to decide if one system is faster than another. I guess my point is the industry is throwing numbers at us that have no meaning in a greater scheme of things. I'm pretty much reminded on the clock speed ludicrosies of CPU marketing, when CPUs were marketed with fictional max frequencies to make them better comparable with our systems. I would love to see standardized tests independently verifiable with a fixed set of tools across ecosystems, like how many tokens does the system generate with a Llama 3.2 3B model, a Gemma 327B, a QBQ 32B, a DeepSeek R170B, or a big Llama 3.1 405B, to throw some sizes. Using a dedicated quantization and a specified runtime like VLLM, Llama, or a combination of multiple others, for me, this is the only reasonable way to compare systems when talking about LLM inference. For gamers, this is already established. Let's do this here as well. I did a comparison like that in my last video to give you an idea how this might look like. Unfortunately, I don't have the means to do that, but I hope the industry or YouTubers with actual resources could use their platform to provide a more transparent view of real-world performance. In case you haven't noticed, that's my plea to the tech YouTubers out there. You know who I'm talking about. To gather and come up with a better way to rank systems for LLM performance. Maybe even you could help me out and make my plea heard by spreading the word. Okay, I think at that point it's clear. We won't be able to definitely answer the question which system is faster in a particular task without actual tests. But there's more that you should consider when choosing your system than mere throughput, the ecosystem you're buying in. Let's start with the NVIDIA Spark machine. One thing you have to keep in mind with this one is that this is not an x86 machine where you can slap your favorite Linux distribution on. It's a custom ARM chip with a special Ubuntu-based Linux distribution coming with dedicated drivers. If you are new to this or only use open source software, that might be a no-go for you. But if you are already using or planning on using an NVIDIA infrastructure, this is a great feature. The Spark fits perfectly into existing NVIDIA ecosystems and allows you to jump from your on-desk task right into large-scale cloud or server deployments, knowing the infrastructure remains identical. This could be a huge speed and confidence boost, not needing to mess around with different software stacks and hardware architectures. When talking about stacks, there is one thing that is worth talking about: the ConnectX-7 Smartnic, built into the Spark. With this NIC, you could connect two Sparks together to use even larger models. This sounds great, but the price of the NIC is insane. You could buy a PCIe version of this card with varying specs starting from like $1,500, but mostly closer to $2,000. Just imagine, the Spark could be even 1K cheaper. That would be actually a great price compared to the competition. 2K, that is cheaper than the upcoming framework PC with most likely a slightly better performance. I think NVIDIA missed out on a great opportunity here by not just giving an option to order without the NIC for a cheaper price. Enough with NVIDIA. What about the rest? I think Apple and their Mac Studio line is kinda annoying. You get this beast of a machine that can do anything in the M3 Ultra, but doesn't have the latest M4 single-core speeds, which is a real bummer. And then the M4 Max is capped out at 128 GB of RAM, so you really have to decide what is more important to you. But I want both. If I had the money, that is. Well, this rant aside, I think at the moment Apple provided the best jack of all trades. You get a more than capable AI machine with a growing community around MLX, a great multimedia general purpose machine, and a huge ecosystem for software and services. With a Mac, you can have it all, if you are willing to enter the ecosystem, of course. I know for some this is a no-go, and that's okay. I get it. I used to point those of you to the Asahi Linux, but with the current state of affairs, I'm not sure if or how this will be going forward. So, well. Finally, we have the new contender in the AI PC space, the Ryzen family of AI chips. Here you get what you most likely already cherish. A lot of options regarding your OS, expansion card options, only PCIe 4.0 x86 chip architecture, and in general a very familiar landscape. The downside, in my opinion, is mostly around the lack of actual driver support and thus performance left on the table. The entry price for the 9HX370 is pretty compelling, but for bigger models this might not be enough regarding performance. I think AMD is a bit of an underdog right now, but this might change very soon. So let's wrap it all up and let me give you my take on things. As we've seen, things are not as simple as they appear to be. Part of the problem are the companies selling products, obviously. However, I don't want you to leave with a wrong impression. The goal of a company is to make money and create great products. Philosophically, I think this view could be challenged, but that's a simple version of it, at least. Are they now to blame for trying to put their products in the best light possible? Although I said it in the past and I will say it again. Your use case matters, and all the products I showed you are really great for a particular type of use case and user. I get it. I'm guilty too. I want it all. I want to get a race car, a buggy, a family van, and a hypercar all in one and for a very low price point. But that's just not gonna happen, at least in the foreseeable future. In sci-fi world, things might be different. But last time I checked, there is no hovercraft I can use instead of a skateboard. So with this wisdom, I challenge you to really think about what you want, what you need, and what you actually want to use. What's your use case and not a fantasy of your use case. I think the systems I showed you today might not be for everyone, but just a couple weeks ago, this market of tiny AI powerhouses that are able to run large language models didn't even exist. And now we have a bunch of options. We are living in the best time ever, and it's only getting better. So think twice about committing unless you really need to. I, for one, will certainly wait before investing in new hardware until I either see valid benchmarks that convince me of solid performance gains, or I can somehow manage to get my hands on hardware for mere testing purposes. But this is highly unlikely. The Spark, as it stands right now, is no longer my favorite. I hope NVIDIA will prove me wrong by blowing my expectations out of the water when the first benchmarks are out, but I won't hold my breath. In the meantime, I think Apple has a very strong offering, especially when looking at the power draw. This is something I certainly underestimated in the past for a machine that is running 24/7. So that's it. I hope you had fun and learned something along the way. If you did, thumbs up would be great, and subscribe if you want to see more. I don't post regularly because I actually have a job and a family, so time is valuable. Anyways, take care and servus.